Here we are back in section 1.1. We're going to continue now with a specific example that's going to be a technique that's going to carry us quite a ways through this course. The exercise we're going to work on is determine if the following system is consistent. If it is, find a solution. This is a system of 4 linear equations and 4 unknowns. And the first is x1 plus x2 plus x3 plus x4 is 4. 2x1 minus x2 plus 5x4 is 1. x2 plus 3x3 is 0. And x2 plus 2x3 minus x4 is 1. Now, this system could be solved using techniques from algebra, fairly elementary techniques of isolating variables, substituting, adding equations together, multiplying equations by constants. But we're going to switch to a technique that's part of linear algebra, and it's going to be a big part of our course. In order to apply this technique, we need something that's called the matrix of coefficients. So we're going to be talking a lot about what a matrix is. Matrix is a rectangular array or arrangement of numbers, sometimes symbols or other things. By the way, the plural of matrix is matrices. And a big part of this course has to do with working with matrices. So the matrix of coefficients means I take the coefficients of each of the variables and write them down. So the coefficient of x1 is 1, of x2 is 1, of x3 is 1. That's from the first equation. Of x4 is 1. In the second equation, the coefficient of x1 is 2. Coefficient of x2 is negative 1. Now there's no term with x3 in the second equation, so its coefficient is understood to be 0. The coefficient of x4 is 5. In the third equation, the coefficient of x1 is 0, of x2 is 1, of x3 is 3, and of x4 is 0. In the fourth equation, the coefficient of x1 is 1. Of x1 is 0, the coefficient of x2 is 1, of x3 is 2, and of x4 is negative 1. All right, brackets around that, and we call that our matrix of coefficients. We're actually going to change this a little bit and write down a slightly different matrix called the augmented matrix. It's the augmented matrix that we're going to use to help us solve the system. We start out with just what we have above, 1, 1, 1, 1, 2, negative 1, 0, 5, 0, 1, 3, 0, 0, 1, 2, negative 1. And what I'm going to do is go back to the system and copy down the constants from the right-hand side of the equation. Clearly, if we're going to solve this system, we need the information that those constants give us. We need 4, 1, 0, 1, brackets around that, and we have what is called the augmented matrix for our system. We think of a matrix as being numbers in a certain arrangement where we have rows going across. Row 1 goes across the top. We have a row 2, row 3, row 4. So 1, 2, 3, 4 rows going across. When we think of the arrangement of numbers vertically, we refer to them as columns. So we have a column 1, column 2, of course, column 3, column 4, column 5. So 4 rows, 5 columns for this matrix. We often refer to a matrix by the number of rows and the number of columns in the matrix. In fact, the row number would always go first, so for this matrix we would say 4. We write an X in between, but we read that as by. Column is 5. So this is a 4 by 5 matrix. So let's just make a general statement here. An M by N matrix has M rows and N columns. The number of rows always goes first, so get used to counting that first. 1, 2, 3, 4 rows, followed by the number of columns goes second. Here we have 5 columns. If I switch the 4 and a 5 around, if I refer to a 5 by 4 matrix, that's a very different creature from what we have written here, because it would have 5 rows, 4 columns. Now let's get into our problem here. Let's start talking about how we're going to solve this. Sorry if that got off the bottom there. We're going to apply a few general rules to help us get through this process. And one of the rules, one of the most important rules, is this: we obtain an equivalent system if we add a multiple of one row to another row. This is actually just the kind of thing you do when you work with the equations and the variables in algebra, and you try to solve the system by manipulating the variable symbols. But we're going to work very abstractly in a matrix to make these changes in the augmented matrix. I'm going to recopy the augmented matrix right here. 1, 1, 1, 1, 4, 2, negative 1, 0, 5, 1, 0, 1, 3, 0, 0, 0, 1, 2, negative 1, 1. And while we're just working with these constants, every step we are going to make now could be in parallel to a manipulation of the original equations. If you look at example 1 in this section in the textbook, side by side they actually show the changes in the equations next to the changes in the augmented matrix. And some of you may find that helpful to help bring this process to life a little bit. Usually students don't have too much trouble believing that, so I'm just going to go right into this process. It's detailed. It's going to seem a bit tedious at first, but it's really not that intense once we get the hang of it. And I think it will also seem a little bit mysterious here when I get started, but once we get closer to the answer, you'll see exactly. I think you'll see a lot better what's going on. So we're going to manipulate these numbers. We're going to make changes applying this type of rule we can make to keep the system equivalent. And we're first going to work on the first column. We want our first column to look like this: 1, 0, 0, 0. I'll say that's what we want. So we're happy that we have a 1 in that first position, but we don't want this 2 here. We want a 0. So we're going to change the second row. Whenever we make a change, we change every entry in a row together. That's how we maintain the equivalence of our system. So So I'm going to take row 2, I'll label that R2, I'm going to change it. Now, to get this 2 to go away, what I could do is I could add to it -2 times the first row, right? Because there's a 1 entry there. So I'm going to take row 2 and I'm going to change it to row 2. I'll write this as -2 times row 1. And down below, we'll show the results of that move. So we're going to do several moves like this along the way, and we're going to try to simplify the look of this matrix till we can see if we have a solution and what the solution might be if we do. Now, I'm not changing row 1 yet. I'm not changing row 3 yet, or row 4. And so row 2, I'm taking an entry in row 2 and subtracting 2 times the corresponding entry in row 1. So 2 minus 2 times 1 is 0, just what I wanted. But now all the other entries will change. -1 minus 2 times 1 is -1 minus 2, -3. 0 minus 2 times 1 is -2. 5 minus 2 times 1 is 5 minus 2 is 3. 1 minus 2 times 4 is 1 minus 8 is -7. So the matrix looks different now. The augmented matrix looks different, but it still stands for an equivalent system of equations. Now, I'm next going to look at the second column, and I'm not going to start up at the top. I'm actually going to jog down to the second position. I'm only going to look at these 3 lower entries. It's kind of like we're going to work our way diagonally from that first one in the upper left-hand corner. We're going to work our way diagonally down. So this -3, 1, 1 portion of the second column, I want to look like 1, 0, 0. I want a 1 in the diagonal position and zeros below it. So this is what we want. And now we're going to start working on the rows to get them into that form. And I like to deal with the -3 first, so I'm going to take row 2 again. And I'm going to change row 2 in a different way. I'm just going to multiply it by a constant. If we multiply by a non-zero constant all the way through, we still have an equivalent system. We basically haven't changed that second equation as long as we multiply through by a constant, same number. So to get this -3 to be 1, I want to multiply by -1/3. And I guess I should write that. This second roll down, we obtain an equivalent system if we multiply a row by I have to say non-zero constant. 0 would change things quite a bit and we'd lose information. So if we multiply a row by a non-zero constant, so that's what we're saying that we're going to do up there. Let's go ahead and do it. First row's the same. So second row, I'm multiplying each entry by -1/3. 0 times -1/3 is 0. -3 times -1/3 is 1. That's really what I wanted. -2 times -1/3 is +2/3. 3 times -1/3 is -1. -7 times -1/3 is +7/3. Recopy. Okay, now I got my 1 in this position. I want zeros below. Remember, I want 1, 0, 0 in those bottom 3 positions. So I'm going to change both the third and the fourth row here. I'm going to take row 3 and replace it with row 3, well, just minus row 2, right? Because if I subtract row 2. And there's more than one way you can go through these steps, so I'm just taking one particular route here. And I'm also deliberately doing only one step at a time for this first example. With practice, you'll see you can often do several steps at once, and it saves you a lot of recopying. 0, 1, 2/3, -1, 7/3. So I'm changing row 3. I'm going to take row 3 entries and subtract row 2 from it. So 0 minus 0 is 0. Right here stays the same. 1 minus 1 is 0 now. 3 minus 2/3 is 9/3, minus 2/3 is 7/3. 0 minus a -1 is +1. 0 minus 7/3 is going to be -7/3. And then recopy 0, 1, 2, -1, 1. Now I would like to get a 0 in this bottom position in the second column. So I'm going to change row 4. I'm going to do the same thing to row 4. I'm going to take row 4 and replace it with row 4 minus row 2 again. These two steps I could have done at once, okay? But not this time. I'll write it out. 1, 1, 1, 1, 4 recopying. 0, 1, 2/3, -1, 7/3. 0, 0, 7/3, 1, -7/3. And now some changes. Row 4 minus row 2. So 0 minus 0 is 0. 1 minus 1 is 0. 2 minus 2/3, 4/3 minus, 6/3 minus 2/3 is 4/3. -1 minus a -1 is 0. 1 minus 7/3 is 3/3 minus 7/3 is -4/3. So the way we're going through this process, we're kind of like trying not to undo what we've already accomplished, like the 1, 0, 0, 0. Then we're not worried about the 1 on top in the second column, but we want 1 in the second position, 0's below. Now we're going to work our way down this diagonal, and it's these two entries that we want to look like 1, 1, 0 now. So it's actually the third row across. I want a 1 in this position. I can replace row 3 with 3/7 times row 3, just to multiply by a constant to get that 7/3 to be a 1. Sorry, I realized I wasn't on camera, so I hope everybody could fill that in. 1, 1, 1, 1, 4, 0, 1, 2/3, -1, 7/3, and now we're going to change row 3. 0, of course, is 3/7 times 0 is 0, times 0 is 0, 3/7 times 7/3. So we're using the reciprocal of 7/3 so that when we multiply we get 1 in this position, and that changes other things. I have to take 3/7 times 1 is 3/7. 3/7 times -7/3 is going to be -1. And then I have 0, 0, 4/3, 0, -4/3 down in the fourth row. Now I got my 1s on the diagonal, but below the 1s I always want to get a 0. So this 4/3 I need to get rid of, and so I want to change row 4. I'm going to replace it with row 4 minus, I guess, since I have a 1 right above it, if I take 4/3 times that 1, that I can subtract from this 4/3. So I'm taking row 4 minus 4/3 row 3. And let's see. I'm also purposely choosing a pretty detailed example here so you can kind of get the hang of this process. If we did one that was too short and simple, I think it would be easy to jump to the wrong conclusions about things. Okay, here we go. Row 4 minus 4/3 row 3. Still a 0 here. 0 minus 4/3 0 is 0. 4/3 minus 4/3 is 0 here. And now we're going to have 0 minus 4/3. Okay, I got to do a little fraction multiplication. That's going to be minus 4/7, I think. 3's cancel. And then 4/3 minus 4/3 times -1 is, or negative 4/3 plus 4/3 is what I'm going to get. I think I get 0 here. Okay. And now, okay, I got my 1, 1, 1 coming down this diagonal. 0's below the 1's. In this fourth column, it's only this one position I want to be a 1. So I'm going to take row 4 and replace it with, to get a 1 here, I'm going to multiply by -7/4, right, the reciprocal. And so it's not going to change much except that one entry. 1, 0, 0, 0, 1, 1, 0, 0, 1, 2/3, 1, 0, 1, -1, 3/7. Now I'll have 1, and recopying 4, 7/3, -1. Now 0 times -7/4 is still 0, so the zeros don't change in that fourth column. Okay, now I just want to pause to take a look at what's happened to this augmented matrix. Starting from the upper left corner, coming down this diagonal, we have 1's. Notice that below those 1's, we have all 0's. Now we're going to work in the area above those 1's. Actually, I should say, let's focus here. Let's think of that one. It's really above the 1's that we've already put in. In this area, we're going to try to get 0's. And so we're actually going to start working above, going through these operations again, but this time from right to left, and we're gonna start in this fourth column, not the fifth column, because that's not a column where we put in one of our 1's. If we had gone further, like if we had another row, we would have had another 1 down here, but we don't, so we're just going to start from this one, and we're going to try to change each of these entries up above. Now I think here I am going to break down and do more than one step at once. Right now I'm just recopying. So I'm going to focus now on this column where our last of those diagonal 1's came from. And we want to get that column to look like, we're going to leave the 1 below, but we want 0's up above it. I'm going to change each one of those at the same time. So for instance, row 1, I can replace with row 1 minus row 4. I can just subtract that 1 from it to get a 0 up there. Row 2, I'm going to take row 2, and let's see, since that's a negative 1, I'm just going to add row 4 to it. So I'm using this 1 here to change these other rows. Row 3, I'm going to replace with row 3 minus, now I can't just subtract 1 because I have a fraction here. I want to make this look similar to 3/7, so I'm going to take minus 3/7 row 4. So in each case, I'm either adding or subtracting a multiple of row 4 to the rows up above. Now, row 1 will change because in each case I'm taking what's already there minus an entry on row 4, but of course 1 minus 0 is still 1, 1 minus 0 is still 1, minus 0 is still 1, but 1 minus 1 is 0. And 4 minus 0 is 4. For row 2, I'm adding row 4 to it, so I'm taking what's already there and adding what's in the 4th row. 0 plus 0 is 0, 1 plus 0 is 1, 2/3 plus 0 is 2/3, negative 1 plus 1 is 0, 7/3 plus 0 is 7/3. Row 3, now this is my more complicated arithmetic here, right? I'm taking row 3 and subtracting a multiple of row 4. So what 0 minus something times 0 is 0. 0 minus something times 0 is 0. 1 minus something times 0 is still 1. 3/7 minus 3/7 times 1 is going to be 0. And negative 1 minus 3/7 times 0 is still negative 1. And I'm leaving row 4, 0, 0, 0, 1, 0. So we're getting there. I'm happy with the look of this column. Next, I'm going to move 1 over. I'm looking up above the 1. The 1's on the diagonal I like. So up above the 1 on the diagonal now, working backwards through the augmented matrix from right to left, I want zeros up above. So I'm going to change row 2, and I'm going to change row 1, applying one of our rules, so I can add a multiple to row 2. Let's see, row 2 I want to replace with row 2 minus 2/3 row 1. I'm using that 1 in this position. Row 1, I'm just going to replace with row 1 minus, I didn't mean to say 2/3 row 1, I meant to say 2/3 row 3. Sorry. It really doesn't matter, but I want to use that 1 I went out of my way to put in. That's sort of the 1 up above we just had by accident. Row 1, I'm going to subtract row 3. Okay. So I have, all right, I'm changing row 1. Row 1 minus row 3. 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. That's what I want to happen. 0 minus 0 is 0. All right, something's changing here. 4 minus the negative 1 is going to be 4 plus 1 or 5. Row 2, I'm going to subtract 2/3 row 3. So 0 minus 0 is 0. 1 minus 0 is 1. 2/3 minus 2/3 is 0. 0 minus 0 is 0. And now I got a little calculation I got to be careful. I got 7/3 minus 2/3 times a negative 1, right? So that's 7/3 plus 2/3 is 9/3, but that's going to be just 3. Yay, back to a whole number. And then 0, 0, 1, 0, negative 1, 0, 0, 0, 1, 0. Okay, so we got zeros up above in the fourth column, zeros up above. Now it's moving back to column 2. I want those top two positions to be a 1 with just 1 0. Keeping the 1s on the diagonal, I'm getting the zeros up above now, working backwards. So this is going to be a pretty easy move. I'm going to take row 1 and replace it with row 1 minus row 2, right? Just going to subtract that 1 from it. So row 1 minus row 2, 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 0, 0 minus 0. Here's a change. 5 minus 3 is going to be 2. And then I have 0, 1, 0, 0, 3, 0, 0, 1, 0, negative 1, 0, 0, 0, 1, 0. And I think I've gotten something. Now, what the heck do we have here? Well, this augmented matrix still stands for equations in x1, x2, x3, x4 that would be equivalent to our original system. So this first equation, now going backwards, remember the first 4 entries were variable coefficients. The last entry is the constant on the other side of the equation. So what do we have? We have 1x1 plus 0x2 plus 0x3 plus 0x4 equals 2. We have 1x2 equals 3. We have 1x3 equals negative 1. And we have 1x4 equals 0. So the system is consistent. Because there is a solution, and it has exactly one solution. So this is some creature in the 4-dimensional world, but there's just one point with those coordinates that's a solution to this system. So we're going to stop this video here, and we'll continue with one more for section 1.1, in which we're going to lay out a few general principles and do one more problem before we're through.